Okay, this is example number 2 for shear stress theory in beams. A bit more complex cross-section beam than the first one. The first one was a simple 2 by 10. This one's a T-shape and says for the T-shaped section below, compute the first moment of area Q as it would be used in the general shear formula. And compute the vertical shearing stress of the section marked AA at the very top of the web, just below it joins the flange. Also compute the shearing stress at AA. The shearing force is 1,200 pounds. So this is drawn a little misleading. They draw AA right there, but actually they want AA right at the transition between the vertical part of the T and the horizontal part of the T. So just to look over the T, its thickness on the web is 1.5 inches. Its total height is 10, and its width up top is 8. They're giving you the centroid of that region and basically the overall centroid, but they don't tell you what the values are. So this is just like a moment of inertia centroid problem that we've been doing all year. In fact, the solution is 95% that, which I have here, and I'll just go through. So up to down here is exactly what we've done for the entire class. If I gave you this question, I said, hey, find the moment of inertia for that cross-section, you could get up to this point, and that's where you'd get. The first part we did was find the centroid. We find it here. The last part we're doing with the shear stress is really only this added area below. I'm just going to go through this really quickly. So we're going to break up the T section into 2 smaller sections. Shape 1, shape 2, and I'm going to make my table, part, area, YI, AI, YI, II, DI, AI, DI squared, II plus AI, DI squared, right? The 3 values we're going to use here, the Y's, the little Y's, if you remember, those are the dimensions between the centroids of the components to the reference axis, the reference axis being here and there. And obviously this shape has one axis of symmetry right through the middle, so we know the centroid is going to be somewhere here. You just don't know where it is. D is the value used in the parallel axis theorem, and that's the dimension of the centroid of the component piece to this overall centroid of the composite beam. And then we got this Y bar value, and that Y bar value is the dimension between the area AP, that's part of Q, right? The area AP from there, what's ever left over, to the overall centroid of the part. So that would be here. Anyway, here's my table. The area, part 1, YI, is simply 9. This times this gives you that column. II is simply, they're both rectangles, base times height cubed over 12. DI, if you're confused how to get that, you can always use this absolute value. And once you get here, you have enough to sum that and do a division and get the centroidal axis location. We find that here. It's 6.86 inches, right? So then you get to the parallel axis theorem. That's this point onward, okay? You can calculate II for the components, okay? DI, if you're unfamiliar, if you're not so comfortable with that, just do this absolute value where it's the centroid location minus YI, right? So it's simply this minus that, the absolute value gets you that. Then you multiply this times this squared, get you that. And then you add this and that, and you get that. And then you repeat the whole thing, and then you summarize this column, and you get the overall moment of inertia for the entire composite section. Okay, and that's what we've been doing all year, and that was on a test, and it'll probably show up in some form or fashion on the final exam as well. Whoa, big bug. Look out. Totally unexpected. Hope I don't freak anybody out with that. That's what you get for working in your garage. Okay, so they give you in the question, they want to know Q. So we want to find the shear stress value right here. Now, we've been saying it before, the max shear stress for this beam is going to be here. I don't know why we won't want to find it there. We want to find it here. So basically, if that's my centroid, here's where I want to find it. What's my area away from the centroid that I want to find it is this. That's going to be my area, AP. So AP is simply 8 times 2, right? Now, how do we find that Y bar? Well, the Y bar is the centroid of that region, right, relative to the centroid of the overall composite beam. So that's from here to here, and that's Y bar, right? So Y bar 1 is only one of them. Y bar is going to be equal to this 9 minus this. So this piece minus this piece gives me that piece. Anyway, you could just figure out the math. It turns out to be 2.14 inches. Here's where I calculate the value of Q. Q is equal to that 16 inches squared times a 2.14. I get a value of 34.2 inches cubed. And then the question asks, what's the shearing stress there? Using the general shear formula, VQ over IT. 1,200 pounds was given in the problem. And if you recall, that's a number plucked off, typically off of our shear diagram. And then Q we just calculated. I is the overall moment of inertia that we calculated earlier for the entire composite beam. And T is the thickness of the beam where you want to make the cut to find the cross-sectional, the shear stress. So we want to find it here. The thickness between the two is simply that dimension TW, and that's what we put there. And we get 114 PSI, and just like we just said, that's not the maximum shear stress, but you can see it's a very low number. So the odds of this beam failing in shear, not real high. Like I said, most of these sections, the bending stress is the more critical. Anyway, that's example 2. I think we have 1 or 2 more, and then we'll wrap it up. Okay, thanks.